So this is looking at a bit more of the theory of regression. So when you fit a line, you can make predictions about the line. So for example, within the data set that we got to do with the pH and time after slaughter, then you can make predictions about the pH using the equation of the line that you've got as a fit. But does this go on forever? Now, realistically, you can only make predictions within the range of the set of data you've collected. So when you do this, this process is called interpolation. So it's between the minimum and maximum value of x that you collected. If you extend the line outside the range of data that you actually collected, this is extrapolation. Now, often we want to do that because that's telling us about the future. So we might have a timeline and we're projecting it to continue to the future. But extrapolation is extremely dangerous. You can predict the growth of human population and extrapolate it to the future. The same as you can extrapolate how you think COVID is going to develop in the future. But the reality is you don't know what will happen in reality in the future because it depends on so many different variables. So in the meat processing example, pH cannot continue decreasing forever. It can't get to zero or a negative pH because that's not meaningful. So it's likely to taper off to some stable level. This means that any regression model is limited to a range of values and you shouldn't try to extend it beyond that particular range. Another thing with regression is you have these confidence bands along the regression line itself. Confidence should always be used in terms of figuring out the uncertainty. So what you can imagine is a sliding window going along the line and you've got a changing level of uncertainty as you go along that line, and these are the confidence bands. Now they actually are wider at the ends and narrower in the center. So when you get to the mean value of x and the mean value of y, they're at their most narrow, and that is where those data points have least effect on the variability of the gradient of the line. So that's what you see in your leverage plots. Possible violations of linearity could be outliers from other populations, or you could just not need a straight line model. So this could mean that you need to do some kind of transformation to the data to get it to be a linear model. If they're not linear, then any estimates you make about fitting this incorrect line will be biased, misleading, and incorrect estimates. But that will depend on the degree of violation. So when you saw the example of the steers and taking the logs or not taking the logs, the differences are so small that you don't see it unless you're taking very great care and doing a lot of the diagnostic work. Transformations can remove these kind of problems. Logarithms, 1/overs, and there's lots of more complicated methods that are particularly applicable to kinetics. Constant variance and normality, these can have an effect on the results in terms of giving you misleading confidence intervals and inaccurate standard errors. These are going to be minor consequences unless it affects the tails of your distribution when you've got the largest leverage, or if you've got small sample size or not very well distributed samples. If these things are true, then problems with your variance and normality are going to have bigger knock-on effects. Standard errors are relatively robust to non-normality, so it's not a huge